Welcome to Lecture 12. In this lecture, we will continue to talk about diagonalization. Recall from the last lecture that we saw that if A can be diagonalized, and remember that will be the case if A has a complete set of eigenvectors, then D is equal to P inverse A P, where P is the matrix whose columns are the eigenvectors of A, and D is a diagonal matrix whose diagonal entries are the eigenvalues of A. And we observed last time that if we pre-multiply both sides of this equation by P and post-multiply both sides of the equation by P inverse, then we get A is equal to P D P inverse, and this led us to the interesting conclusion that A to the nth power is equal to P D to the nth power P inverse, where n is a positive integer. We saw this in lecture 11. And we noted at that time that this is a handy thing to know about because raising some arbitrary matrix A to the nth power might be quite a bit of work. But for a diagonal matrix, it's very simple to raise a diagonal matrix to any power, because that simply consists of raising each of the diagonal terms to that power. So this is a potentially very useful technique to know about, but you might wonder if it is even more general than we have here. In other words, you might wonder, does n have to be an integer? And the answer is no. For instance, A raised to the 1/2 power is equal to P D to the 1/2 power times P inverse. Again, where the assumption is here that this won't work for any matrix. It has to be a matrix that has a full set of eigenvectors. But if A does have a full set of eigenvectors, then the square root of A, in other words, the matrix that can be multiplied by itself to give A, can be calculated in this way. You find the P matrix, which remember is the eigenvectors of A, and you find its inverse, and then you find the D matrix, which is simply the matrix whose diagonal elements are the eigenvalues of A. Then take the square root of that and multiply it all together, and you get the square root of A. So let's look at an example of this. Let's let A be the matrix 24, -10, 30, -11. And we want to find a matrix, we'll call it B, such that B multiplied by itself is equal to this A matrix, or in other words, So b is the square root of a. Maybe I'll just write it as a to the 1/2 power. Now, so if we are claiming above that if A has a complete set of eigenvectors, then B is equal to P D to the 1/2 P inverse. So let's take that approach and see what happens. Now, in order to find P and D, we need to find the eigenvectors and eigenvalues of A. So let's go about this in the usual way. So we'll say to find P and D, we must find the eigenvalues and eigenvectors of A. And of course, the way that we do that is by setting the determinant of A minus lambda I equal to 0. So we get 24 minus lambda, negative 10, 30, and negative 11 minus lambda is equal to 0. And so this gives us 24 minus lambda times negative 11 minus lambda minus 30 times negative 10 is equal to 0. So we get lambda squared, and then we have negative 24 lambda plus 11 lambda, so minus 13 lambda, and then minus 264 plus 300, so that's plus 36, equals 0. And this can be factored into lambda minus 4 times lambda minus 9 is equal to 0. And therefore, our two eigenvalues are lambda equals 4 and 9. So I will call lambda 1, I will call 4 lambda 1, and 9 I will call lambda 2. And so now we want to find V1 and V2. So, of course, we know how to do this. AV1 is equal to lambda 1 V1. And so, reminding ourselves, 24, negative 10, 30, negative 11. 24, negative 10, 30, negative 11. Times x, y equals lambda 1, which is 4, x, y. So this gives us 24x minus 10y is equal to 4x, and 30x minus 11y is equal to 4y. So the first equation will give us y equals 2x, and as well as the second equation, it gives us the same result. and therefore we can choose V1 is equal to 1, 2. And of course, you could easily check and make sure that that this really is an eigenvector of A with associated eigenvalue of 4. But I'll leave that up to you. Now let's look for V2. We get A V2 is equal to lambda 2 V2. So 24, negative 10, 30, negative 11, x, y is equal to 9x, y. So 24x minus 10y is equal to 9x, and 30x minus 11y is equal to 9y. And so now if we do a little bit of work on this, we get y equals 3 halves x for this first equation, and for the second equation, again, y equals 3 halves x. So we can pick V2 equals to 3. And therefore, our P matrix will be 1, 2, 2, 3. Now, if you use the Gauss-Jordan procedure, you can find out that P inverse is equal to negative 3, 2, 2, negative 1. And of course, D here is going to be equal to lambda 1, which is 4, 0, 0, 9. Now, recall that our claim here above is that B is equal to P times D to the 1/2 power times P inverse. So let's copy that down here. B is equal to P D to the 1/2 power P inverse. And so this would become 1, 2, 2, 3, and then D to the 1/2 power. Since D is a diagonal matrix, it's easy to take its square root. You just take the square root of each term along the diagonal. So we get 2, 0, 0, 3. And then P inverse is negative 3, 2, 2, negative 1. And so let's see what we'll get here. When we multiply the first matrix times, well, multiply the first times the second, and we will get 2, 6, 4, and 9, and then that gets multiplied by the last matrix. We'll just bring it over. And now when we multiply out those two matrices, let's see what we get. 2 times negative 3 is negative 6, and 12 will give positive 6. 2 times 2 is 4, minus 6 is negative 2. 4 times negative 3 is negative 12, and 18 gives us 6. And finally, 4 times 2 is 8, minus 9 is negative 1. So we are coming up with a conclusion that B is equal to 6, negative 2, 6, negative 1. And now let's check to see if B times B does indeed give us A, because if B is the square root of A, then B times B should give us back A. So let's check and see. 6, 6, negative 2, negative 1, times 6, 6, negative 2, negative 1. And this will give us 6 times 6 is 36, minus 12 will be 24. 6 times negative 2 is negative 12, and 2 is negative 10. 6 times 6 is 36, minus 6 is 30, and 6 times negative 2 is negative 12, and 1 is negative 11. And sure enough, if you compare that to what we have above, you see that that is indeed 24, negative 10, 30, negative 11. That is indeed the matrix A. So we see that this technique of diagonalizing and then doing the appropriate operation on D, it works even if n is not an integer. And so this is a very interesting way to calculate the square root of a matrix. So now we'll just have one problem related to that procedure. So the problem I'd like for you to do, just one problem here on this lecture. We have the matrix A, which is equal to 43 minus 13.5, 36, negative 2. Use the technique shown above to find the square root of A. And that's it. That will conclude lecture 12, and good luck.